What was the prompt?
Sorry?
What was the prompt for this one?
It was like a condensed version of the abstract.
Wow! Is this what you guys were thinking about when you wrote the paper?
That's the vision that came to me in my dreams.
Yeah.
Can you talk about and interpret the essential dynamics block of this?
This is the essential dynamics block.
It's not a plot, it's the thing itself.
Yeah. All dimensions.
Yep.
This is a pipe.
Pipe.
Reference to this is not a pipe, the painting.
What is it? This
I don't
is
know
the
the
what?
painting.
I don't know the painting.
Wait. This was. Indeed, this is essential.
We'll give it
Mm-hmm.
just a few minutes.
Because Tom is speaking.
Oh, right.
Yeah. The clash was never resolved, was it?
This. This is not a pipe. That's what that says.
Oh.
This is essential.
Is Tom speaking from
It's
9 to 10?
yeah,
Or
no,
9
it's
to
9:30.
9:30, 10:30.
What's he speaking about?
Interagent danger using grid roll. Is that grid rolls?
You know how if you like plug random stuff into diffusion models, there's like certain types of regular shapes that come out of it?
Yeah, no, that.
I've spent like a while with like mid-journey and stuff doing this, but I'm curious if anyone's like written papers on like sort of like the default, if there's like default patterns or structure that come from just like mashing out of distribution stuff into it.
What do you use to make your images like that?
I once upon a time made one of these custom GPTs.
Right.
And I use that as well.
Is your laptop not Carroll?
Sure it does.
Is this being recorded?
It is. Unless you'd like to put it in which case I'll stop.
I think we can handle it.
Handle the recording. Although it is a very weird angle on that camera, isn't it?
Yeah, if you stand right there, your head will be repeatedly blocked by the light.
Oh, did the lights come down again?
No, it's just that light
Yeah,
picture
no,
placement and that camera placement just don't work together.
Yeah, because we made a little look at the
we tried to fix also
That is.
That's
Manipulation may be
not
okay.
it.
Yeah, manipulation may be okay.
I know.
So, but the
Yes.
the loop has
Yes.
shrunk, so it might need to be relooped.
Just add a second loop.
Yeah, it looks like you should be okay.
Yeah, someone said on this.
Is this okay or should I come
This is here.
It looks like you just
Feels
barely
so.
Is there a way?
I don't want to do that. No.
I'm happy to do it again, but is it fine or should I do it?
I think
It's fine.
Did you stand on the chair last
It's
time?
fine.
Yeah.
It's just barely fine, but it is fine.
But just like stand, stand like on the
Just on the edges,
Stand on the other side.
Other edges.
Yes.
Tiberia's like flashing before his
It's not work much.
Make a knot.
It's
a knot.
let's okay, it's fine as it is. It's fine as it is.
Yeah, leave it.
The recording is already
Leave it.
fine as it is.
Someone feels a strong urge to improve it. Here's the thing.
No,
Okay.
that was good.
But I think it's fine. But I think it's fine.
Alrighty, let's get started, I reckon. Cool. Good morning, everyone.
Good morning.
Thank you for coming along nice and early. Seems like the mornings have been getting later and later.
Yeah.
here at 8 a.m. this morning, and it was just me and Dan shooting the shit. So, my name is Carroll. I am a researcher with Timaeus and the Gradient Institute, and this morning I'm going to tell you a little bit about some work that we've been doing on transformers trained on linear regression, and an interesting phenomenon that we have observed, which we are terming retreat from ridge. We're not the only people to observe this phenomenon in a certain sense, but it's still a very interesting thing, and the tools that we have at our disposal with singular learning theory and also essential dynamics, which I will introduce, help to cast some new light onto what's going on in this very interesting setting. So this talk is about a paper that will be on the archive very soon, very soon. We've been so close for about a month or so, and I reckon hopefully after this week we'll get it done nice and quickly. So the paper is in collaboration with Jesse Hoogland and Daniel Murfitt, and yeah, we will share it around once it's up there in a few weeks. So to go back to Jesse's introductory talk the other day, we are interested in this question of what structures are present in data, and therefore how do those structures affect the development of a model over the course of training, and in what way does it learn those structures. And you can think of structure, of course, in many different ways, and it's a very ill-defined kind of concept at this moment, but as a starting point you might think of something like bigrams in language as an example of a structure. And then, as Jesse was saying, what we have observed in AI over the last few years is something more like in-context learning, which represents a kind of algorithm that is present in the data, that is latent in the data. And so this is a very interesting fact, right? The fact that transformers can adapt their behaviour in context and effectively learn how to perform a certain task in the context is obviously a very interesting thing that we want to understand. And so this work is really motivated by this question: what algorithms are latent in the data? And the reason that this is important, I'm sure this will be very intuitive to most of you here, since this is an AI safety conference, but the idea of misspecification, where we think that the training data contains this thing, but perhaps the model is actually learning something that generalizes beyond the thing that we think we're putting into the data. So could there be unintended learning algorithms that we are actually accidentally sort of asking the model to learn, in a sense, that we, the trainers, did not actually intend to be in there? So these kind of algorithms could be invisible to evaluations. This is a big concern within AI safety, just because you've seen that the model performs on a set of naughty data in XYZ way. Does that mean that it's always going to perform in that way, or are there actually algorithms that are lurking underneath that could be exploited in various ways? And so we want to understand, how can we understand the generalization properties of a model under distribution shift? What happens when we change the inputs that we are feeding into the model at deployment time compared to what it was trained on? And so this work is really motivated by this question. So in 2023, Reventos et al. Released this paper called Pre-Training Task Diversity and the Emergence of Non-Bayesian in-Context Learning for Regression. And it's a really good setting. It's building on other linear regression setups. I think Garg et al. In 2022 might have been the first to present this kind of framework. And the reason that this is such a great setup that Reventos introduced here is that we can see two different algorithms that a transformer could be implementing in order to perform this linear regression task. And what Reventos et al. Show is that as you shift the data distribution by increasing the number of tasks in that training set, there is a change in algorithm at the end of training. And so you can see here that the orange curve represents the end of training model, and you can see that for some task diversities M, it follows what I'm going to refer to as the DIMS algorithm. I'll explain this a bit later. It follows the DIMS algorithm for a while, and then suddenly it starts to jump towards something more like the ridge regression algorithm, and we put our SLT hats on and we stare at that jump and we go, that looks a bit suspicious, because the optimal solution is always this DIMS algorithm, the Bayesian optimal solution, and yet you see this jump which has these sort of signals of phase transition lurking beneath. So this was the starting point for the work.
But can you just explain what the dims and the ridge
I
are?
will get to that later. That's a key part of the talk.
Would you also cover how you know which algorithm the model is doing?
So in this work, they are just taking a square distance between the model's predictions and what the algorithm itself would predict. And so that's essentially what these deltas are saying.
And the algorithms would predict different things or something?
Yes.
Therefore you can tell.
Yeah.
Okay.
Exactly. So I'll explain what the algorithms do.
Okay.
But this shows you how that shifts at the end of training according to changing the true distribution underneath. And then earlier in the year, I was a co-author on this paper led by Jesse Hoogland and Daniel Murfitt, that the developmental landscape of in-context learning, and we analysed here stage-wise development of these transformers trained on linear regression, but just in the setting of m equals infinity. So just in the infinite task distribution, which I will explain a bit later. But here we looked at the local learning coefficient, and we were able to detect stage boundaries according to according to the LLC curve, and much like what George presented with the language models the other day, we were able to detect stages using this and corroborate that according to some other measures as well that showed that various things were happening at these stages. So this work then poses the question, what happens when we combine the Reventos et al. Stuff with our stage-wise analysis, stage-wise development analysis from the developmental landscape paper. And so we want to understand what is the nature of this negotiation between two algorithms over the course of training. And in particular, this would give us an insight into what the geometry of the loss landscape, how that is affected by shifting the true distribution. So this goes towards the idea of structural generalization that Jesse mentioned the other day. How robust are certain algorithms that the model is learning under distribution shift? So the key observation that I'm going to talk about this morning is that over the course of training, we see that there is a certain band of task diversity M values for which the models undergo this so-called retreat from ridge, something like a retreat from ridge, where they start to aim towards a generalizing solution generalizing in the sense of being able to perform well on tasks that are not included in the training distribution. And then we will see that they start to pivot at some certain point towards a memorizing solution, the DIMS algorithm. And so we have two key tools. Essential dynamics helps gain insight into this training trajectory in function space, and so essential dynamics reveals this phenomena and really helps paint the picture of what is happening. And then singular learning theory, by measuring the local learning coefficient over the course of training and at the end of training, we can make sense of why this retreat from ridge might actually be able to happen in the first place. So the aim of this talk is to understand these two plots.
Sorry, maybe everyone knows. What's essential dynamics?
You will find out soon. I will introduce it. These are the two tools. This is the aim of the talk. Understand these two plots. So I'll start with the setup of the linear regression problem and then explain our essential dynamics technique and how we implement it, and then have a look at how singular learning theory helps us understand what's going on. So, linear regression. Suppose we had a latent linear regression task T, which is just a vector in d-dimensional space. We can sample some input from a normal distribution and some isotropic noise with a very small variance, and then generate and then generate an output y according to that task vector. So the task times x plus the noise. That of course gives us a y value there. And then we can do this k times and generate a data set of pairs. let's just say that again.
How long did you spend on that video?
I'm not gonna talk about it.
Never ask those questions. So we generate k different pairs according to this latent linear regression task, and that gives us a context. So in this work, I'll just state this here, we are going to use a regression dimension of 8, d equals 8, and a context length of k equals 16. So
To be clear, that would mean 32 tokens, as in 16 pairs of x, y.
yes, yeah, I'll explain the tokenization in a sec, but 16 pairs of points.
Okay. Thanks.
So what does it mean for the transformers to be trained on linear regression on this setup? Well, we suppose that there is an underlying task, the t vector, and the transformer first just sees x1, and they are asked to predict what is y1 based on that x1. And of course, at the start, it's going to have no idea what the underlying task is, unless it's perhaps only been trained to perform one task, at which point it's going to know, or it's always going to know, but essentially you should think x1, I don't know, I'll take a random guess. So takes a random guess, and then of course it's going to have some loss on that, and then for the next token, we are now feeding in x1 as well as the true y1, and then asking it to predict on the next x2. So transformer predicts, purple dot down the bottom there, again very far off this latent linear regression task, and we can then feed in the actual y value, calculate the loss, and so on. And so we start to build up these pairs, and And we are asking the transformer to predict on each subsequent pair given that it has seen 1, 2, 3, 4, 5, etc. And so then we finally query it on the last x value, and by this point it should, hopefully, if it's doing a good job, it should have inferred what is the underlying task, and it should make a pretty accurate prediction. So we might guess that it would predict perhaps even on the line, and then of course there's always going to be a little bit of noise, so it's never going to be a perfect predictor, but it likely will infer the underlying task. So we encode this problem as a tokenized context with masked attention, and so each pair, the x value represents a 0, and then so the outputs here, the y values are all single dimension. I forgot to say that, but here each column is a 0 and then 8 rows representing the x, so d rows, and then a single y, 0 vector, etc. And so the transformer is just being trained on these y values here. How well is it predicting those y values? Cool. So, yes?
Just to confirm, that means that the transformer is seeing a regression task. It's not a categorical. It's not being like binned and quantized, or are you saying it is?
What do you mean by binned and quantized?
Is the transformer seeing a one-hot, like, magnitude levels, or is it seeing a single dimension of that varies linearly with the magnitude of?
The loss is like MNC, right?
Yeah.
So it's not.
There's
It's not quantized.
It's not.
So we can set up a task distribution, which is to say we can sample m of these linear regression tasks from a normal distribution and construct a finite set of tasks here, T1 through to T capital M. So the training distribution corresponding to this task distribution, what that means is if we were to sample a context from this training set, we first sample a task from the set of tasks and then generate a context according to what we saw on the previous slide. In the case of m equals infinity, this just means that each context that is sampled has a different task vector that is just sampled from the normal distribution at training time. So, just to give some intuition here, if we have a finite set of tasks, you can think of it as perhaps the model is able to store all of these different tasks. It learns that there are 4 in the underlying set. And what I want to convey here is that it doesn't take many data points, potentially, it doesn't take many data points for the transformer to learn which task it is seeing in context. So, you see that blue dot there and you go, don't know, it could be any of them at this point. You see a second and you're like, yeah, okay, maybe it's T2, maybe it's T4, looks like it could be close to either. But then you see another one and it's like, that looks pretty good, right? So even though this is an 8-dimensional vector, it might not need many XY pairs in order to have a pretty good idea of, yeah, I know it's definitely this one that I have learned. So you can continue along. Whereas if the training distribution was the infinite task case, then we've got a bit more of a problem, right? Because I give you a data point, what task are you going to infer from that single data point? Well, not very much. I give you a second one, and remember we're in 8-dimensional space here. I give you a second one and you go, oh yeah, okay. It's going to take a while before you can actually hope to infer what that task would be.
Even with just 2, you will have a clear best guess, which is just like the
Yeah, but it's probably not going to be very
Oh yeah,
good.
if you have high error bars.
So this is kind of the intuition for two different regression algorithms that one can prove are Bayesian optimal in the finite case and in the infinite case. So when the underlying task distribution is finite, then the discrete minimum mean squared error is shown to be Bayesian optimal. This is shown in the Reventos paper. And essentially, how you should read this formula is that suppose it learns the underlying tasks in Tm, then for any context that it is seeing, it's basically going to go through each of those tasks and evaluate how good is the fit for this task to the data that I have seen, and then it's just going to take a weighted sum of those tasks according to the softmax distribution there. So I think the easiest way to understand this is if you've seen enough tokens, then this softmax is going to concentrate on the correct task. If you are seeing a context that comes from the underlying task distribution that you know. And so essentially this is going to pick out the right task vector from the underlying set. In that sense, it is a memorizing solution. It is memorizing the task underneath and picking them out at inference time with a long enough context. On the other hand, for the infinite task distribution, the Bayesian optimal solution is the classic ridge regression, which is ordinary least squares plus the regularization parameter that comes from your Bayesian prior, effectively. And so in this sense, ridge regression is a generalizing algorithm. It can perform well on tasks that are not necessarily, it can perform well on any task from the normal distribution. So importantly here, DIMS, the discrete minimum mean squared error, is not going to perform well on out of distribution tasks if it's a finite set, but ridge regression can still perform well. Two things to note. The DIMS algorithm does converge to the ridge algorithm as the task diversity goes to infinity. And also, if you are seeing enough tokens, if K is large enough, then these two algorithms are going to predict very similarly as well. The real question is what happens with only a few data points in the context. That's where the distinction lies between the two of them. So the reason to study this is that it is an ideal setup for studying how perturbations in the true distribution, the training distribution, affect the geometry of what we are seeing, the geometry of the training trajectories. And so what we do in this paper, we essentially build up a set of, or a sequence of different task distributions that are each supersets of the last. So we start with just one task, and then the second model is going to be trained on two tasks, but it includes the first task there, so on, making the training distribution larger in a sense. So we train one model per m value in this family here. The first set is because essentially Reventos observed interesting phenomena as you increase by an exponent of 2, whereas we've also included some other ones just for a bit more resolution, which you'll see in a bit as well. And we've also included the m equals infinity distribution. And so this leads us to the key questions of which algorithm is chosen for each training distribution, and how do these perturbations affect the developmental trajectory. Alright, any questions before I head on to the essential dynamics? Great. Alright, so we want to take our transformer model, here represented by a function f, which takes input, has a parameter space w, and produces an output. Ideally, we would like to understand what this function is doing for all inputs x, right? But of course, these functions are extremely complicated, and because of the nonlinearities, function space therefore becomes infinite dimensional, which makes it very hard to understand what is this function doing for all of the inputs. So, one way of approaching this is just to evaluate it on a bunch of inputs. So, take some inputs x1, x2 through to xb, and here these x's are just inputs to the transformer. It's not the same as the x's that were in the regression setup. So just notational conflicting there, but that's alright. So, alright. We want to understand the function, we feed in a bunch of inputs, we take out a bunch of outputs. And so we can construct a vector that just consists of the various y values here. We want to understand what is this curve. We can just take some finite dimensional projection of that. Then we can ask the question, well, how does the function change over the course of training? In other words, what is the trajectory in function space of this model? And so to do this, we can then evaluate the function on these inputs over many different time steps over the course of training. And so in doing this, we are essentially tracking each of these outputs as a way of understanding what is the underlying, how is the underlying curve changing. So the problem is, if you construct this matrix like I had on the previous page, we're going to take 512 inputs and f is going to produce 16 predictions, so it becomes quite a few columns. And also we want to look at it over many different time steps. In these training runs we use 150,000 time steps, although we checkpoint them at much smaller intervals. And so the idea of essential dynamics, which is introduced, at least by that name, in Amadei 1993, which is a molecular dynamics sort of field, is where it originally came from, in a sense. The idea of essential dynamics is to apply principal component analysis to this matrix tracking the trajectory. So we obtain a singular value decomposition of the matrix, and that is done by getting the eigenvectors of the covariance of the trajectory, and then principal component analysis says, well, you can order those eigenvectors according to their eigenvalues, their singular values, and those singular values correspond to the explained variance of those eigenvectors. And so if you order them up, then projecting onto the first v eigenvectors, in this case 2 eigenvectors, will contain the most variance that you could hope to get from just 2 vectors. So in this way, we are able to obtain a lower dimensional representation that captures the essential aspects of the trajectory. So, oh yeah, and just to say as well, this is a very natural thing in mathematics to study. Studying the modes of this kind of trajectory is a very natural object and quite a common thing to do in signal processing and stuff. So just to give a visualization of what this looks like, we take a bunch of raw signals, which are all different columns along there, that represent different outputs over the course of training. And then we apply PCA, and we get a lower dimensional representation in the essential subspace. So here we're just taking one model trajectory, and we transform all of those signals. I think there's like 8,000 columns. We transform them single trajectory through the space. Yes, Zach.
Just to be clear, the x-axis are different there, right?
The x-axes are different. Yeah. This is in principal component space. So PC1 along the x-axis and PC2 along the y-axis.
Then how would I interpret the graph there?
So you would interpret it as saying that it starts at a point up here, initialization, and then the trajectory travels through PCA space or PC space as such. And so you might stare at that and say, perhaps something interesting is happening at that turning point. Perhaps. I'll explain in a second that maybe not as well.
The time steps are uniform. So the trip lines are uniform in time. Is that correct?
No, they're not. In this work, we use logarithmically spaced steps and linearly spaced steps, and in the paper, I've got a few plots that show how that influences the trajectories.
Okay. Yeah.
Is the x on that plot the start or the end?
The start.
That's
Alright. So that was normal essential dynamics, but the problem is in normal essential dynamics you often get these so-called phantom oscillations, which can be called Lissajous curves, or at least deformations of Lissajous curves. And the reason for this is that when you are feeding in time signals into PCA, time is a very, very strong driver of that data. And so essentially, when I say Lissajous curves, what that is saying is that the PCA is basically picking up on time as an organisational, as organising the data in some way. And so you sort of run this analysis through, and in these works here, Shin 2021 and Antropini 2018, as well as Hess 2000, I think, they show that if you apply PCA to Brownian motion, you just get Fourier modes. And so the lesson here is that if you just apply PCA to a trajectory of any kind, you're probably not going to see interesting behaviour. You might see something, you might see some kind of stage, but you need to be wary.
So first, you're doing PCA on the function's behavior on a few points at each fixed time step, right?
Yeah.
And then you're identifying the first principal component at one time step with the first principal component at the next time step. So when you draw these curves, you're just linking them that way. Is that right?
No. So the PCA will transform this 8,000 dimensional vector for each time step. That will then become one point in the PC space.
Right. That's sorry. Maybe I still don't know if I'm misunderstanding or if I just spoke poorly. You are doing a PCA at each time step or not? An individual PCA at each time step?
No, doing PCA on the full matrix there.
The entire trajectory.
The rows and columns.
Yeah, so the PCA reduces the dimension of the columns. The rows indicate the time steps. And so each one of these vectors turns into a point in two-dimensional space, which is then plotted as one point here. So you have a trajectory, point, etc.
See the matrix of vectors and you're reducing the vectors and it's all function.
I understand that.
Are the points that you're like plugging into the function, are these like held out points from the training distribution, or?
I'll explain that.
Okay.
So, normal PCA on just a single trajectory is kind of boring, but actually this becomes a really useful and somewhat powerful technique if we think to compare trajectories that are being evaluated on the same data. So, joint essential dynamics takes all of our training runs, all of our training trajectories, and asks the question, what is the comparison between their trajectories in the same essential subspace? So, joint ED applies PCA to the concatenation of the trajectory from the first training run the trajectory from the m equals 1 distribution, the trajectory from the m equals 2 distribution, and stacks all of those things. Importantly, the feature space of this matrix must be the same. So you can only do this if you are comparing the trajectories on the same data set. But you can stack any process that you like along the sample axis there. So you could, for instance, maybe you're not changing the training distributions, but maybe you are just running many different random seeds on the same process, and you could perhaps use this technique to spot like a bifurcation. Is the training trajectory always doing the same thing, at least according to the essential subspace?
So, Tika, the axis you're stacking on, is it like you're sort of taking the samples from one run with one task, and then you continue, and now it's the second run on another task? Like, is it on the training sample axis?
On the training time axis.
Training time axis, yeah.
Column wise. So in the work, if you think back to what I was saying about the task distributions, we stack these task distributions, right? They become larger for each distribution, each training distribution. And so, well, what is the natural data set that we could compare trajectories on? The single task data set, because that task is included in all of these model trajectories, all of these model training distributions. And so that is exactly what we do. And the result, yeah, I've stared at this picture quite a lot. So this picture has quite a lot of content in it, but I think I would also just like to emphasize here that I think of this joint essential dynamics tool as a window into the training trajectories and their relationship to the perturbations in the true distribution. And by window, I mean, I think that you can infer things from this that help guide your further analysis and tell you, well, maybe this is happening here, so maybe I should be thinking about this. Maybe this principal component is talking about these data points, so I should think that maybe something's happening here. So let me explain what we see here. Each model is initialized at the same point in parameter space, and then each curve represents a different training distribution, but all evaluated on the single task distribution. And you can see that at the very start, when it's just one task, it's nearly just a straight line from initialization to the diamond over here, and each of these diamonds represents the different DIMS algorithms conditioned on training distribution TM. So we can see that these algorithms form nearly a straight line, which is kind of interesting. The principal component space has sort of naturally organized these algorithms, and you can see that, as we said, the DIMS algorithms do converge to the ridge algorithm down here in the bottom. So we take the sorry, you guys out.
Yeah, so you're plotting the DIMS and ridge algorithm in a PC space by evaluating it on the same data points and then projecting it onto the principal components.
Yes.
Yeah.
Exactly. So we see at the start here that for a very small task diversity, there's not very much that's interesting about these trajectories. But then for task diversities sort of 6 upwards, we see that at first they start to go, they're sort of aiming towards the more generalizing ridge solution, and then at some point they pivot and they go, actually no, I can specialize, and they start to go towards the memorizing solution. This is most pronounced in these M values down here, which truly are kind of aiming right for ridge, and then it's only at some time step where they go, nah, I can go and memorize over here. And then we see that for m values past 256, the trajectories are extremely uniform and they're basically all just going straight down to ridge.
How do you define secret?
Right, good question. So, let me show you the next slide and that will help define. So I'll come back to that. If we look at these PCs,
For task 2, is it the same vector as task 1 plus another random one, or is it 2 different random ones not shared with task 1?
the first thing you said.
Okay.
So if we look at these PC curves over time, because time is the sort of parameter that is underlying all of those curves that we saw in the previous one, when you look at that plot there, what might you think this resembles? So it might be the loss curve, and it turns out it's basically identical to the loss curve. So it turns out that PC1 is essentially detecting the loss curve as the predominant signal of the data, and it's pretty amazing how similar these two are.
Is it loss curve on their own training data or loss
No,
curve
on the single task data.
Right.
Is the first principal component PC0 or PC1?
PC1.
Does the interpretability of these principal components, do you think, depends on the fact that you're literally doing linear regression and not even a little bit more complicated task? Just because principal components all about linear understanding?
I would say that the structure we see in the DIMS solutions potentially has something to do with that, but I think this kind of result would generalize beyond just linear regression. So if we look at PC2, we see that at various time steps, we see that the curves for various m values in the middle band here pivot at a certain time step, and that time step increases as m increases, and it turns out that these coincide with precisely where these models deviate, or where these models have a turning point in their loss on the infinity distribution. So they first learn something that can do better on all tasks, and then they specialize and they get worse on that. And that is a pretty interesting phenomenon. And especially at these m values down here, they really are going towards ridge and then they deviate. So, what is driving this retreat? Well, if we have a look at the per token loss at the end of training, we start to get a sense of what is distinguishing these two algorithms. And as I was saying before, intuitively, it's these middle tokens which DIMS can predict pretty quickly or pretty well, whereas ridge will require more tokens to predict well. And so that's exactly what this plot here shows. Up till about 2 to the 7, the model at the end of training is predicting very similarly to DIMS, and then we have this big jump where it suddenly looks a lot more like ridge there. And importantly, it is these sort of tokens 3 and 4 that are the biggest distinction between the DIMS algorithm and the ridge algorithm. And so if you look at the loading matrix of the PCA, which is essentially encoding the importance of each feature in that principal component, if you average those over each of the examples and look at something that is essentially kind of like the correlation between token index and principal component, we can see that it is these middle tokens 3, 4 and 5 that show up the most in PC2. There's also this really stark fact that PC3 is really caring about the first token. So I don't have plots that look at that here, but you can basically see that the PC3 curve is very similar to a curve that shows how close is the transformer to predicting basically the zero vector for the first input, which is just the prior distribution. So in this way, the essential dynamics starts to give you a sense of what is changing as we vary the true distribution and how that signal is encoded in the features. So, in summary, we do see a retreat from ridge for these m values, and there's a critical m value of 256 where they appear to just go to ridge and then stop there past that m value. And so it's really worth emphasizing here, for m equals say 512, there are only 512 tasks in the underlying distribution, and yet it has learned an algorithm that is able to perform on many, many more. This is the sense in which this problem is really great for studying out of distribution generalization. We thought that we were putting this into the transformer, but actually it has learnt something broader than that. And then I'll just put these there. Yes?
To which extent do you think essential dynamics can be used like more widely for like bigger systems, and how expensive is it? Like
not too
do you do this
expensive.
for like a bigger transformer or something?
It takes like, this was like an 8,000 column by like 42,000 row matrix for very big training trajectories, and it takes like 30 seconds on my MacBook. So
on that.
yeah, and I think it's a very powerful technique for comparing trajectories that are related in some way.
I think Anthropic's induction had.
Yeah, so Anthropic used PCA in the induction heads paper, but they only looked at a single trajectory. And so if you look at it from the point of view of the Lizard curve phenomena I was talking about, you're kind of like, I don't know if it really says that much. But this, I think, says a lot more when you're comparing them in the same space. So I'll just emphasize as well that the turning points of the L infinity loss do coincide with these turning points that we see on the plot here. So that is what those dots are being defined as, and it is not clear a priori that that has to be the case. So the PCA really is picking up on these modes.
How does T critical relate to when you start to see a repeat of tasks?
I might think about that and come back later. I might just hold off on questions for a bit just so I can get through the SLT stuff in the last 5 minutes or so, and then happy to answer. And I'll just put here my favourite plot, which was banished from figure 1, which I'm devastated about, but that's okay. I think it's really beautiful seeing the sort of uniformity of structure, and I think that this really gives you quite an interesting window into how these trajectories are changing with the distribution. Like, there's a lot there, right? What signals are they picking up on? That is the question. Alright. So, how might SLT tell us something about this? Well, if we just sat down and thought about it for a sec, we could say that the loss that the DIMS algorithm, or let me go back a step. Suppose that our model architecture was just so big, so good that it could represent both of these algorithms perfectly. That's not the case, but just suppose for argument's sake that that was true. Then we would imagine that DIMS is always going to be a better solution than Ridge, but as you need to increase the number of tasks that you memorize, its complexity, its local learning coefficient, is going to increase past some value of lambda for Ridge. So if you run this analysis through and we set up our favourite free energy formula, then you can start to make a few predictions for phase transitions that you might see, at least in the Bayesian sense, where the phase transitions are with respect to the number of samples, n. So you would probably predict that for very small n values, there is going to be no phase transition because DIMS is always going to be preferred. It's very low loss and it's very low complexity. But then, for this middle band of n values, we would predict that there is some critical value of n where the free energies do switch their order. And then, to the extent that the Bayesian phase transition picture is reflected by dynamical phase transitions, we could then say that this predicts that the transformer is first going to go through the more generalizing solution with higher loss but lower learning coefficient, and then specialize and go to the lower loss memorized solution with a higher learning coefficient afterwards. And then past some critical value of m, we would expect that the lower complexity ridge is going to be preferred, at least insofar as we only have a finite training time that we can evaluate on. So, using all of these predictions, we could guess that perhaps the learning coefficient at the end of training is going to look like that solid curve there. And then the question is that experimentally verified? Yes. That is indeed what we see. So, I obviously don't have too much time here, but this plot really does represent what we would naively predict based on that previous slide. And so we see that the learning coefficient at the end of training does start really small when it's only memorizing a few tasks, but then it does pass ridge at 2 to the 4. And so exactly in this region here is where we would expect the retreat from ridge to really truly happen, because it is first going to learn the more general ridge solution and then overtraining go towards the specialized solution there. And so these are the LLC curves over time corresponding to this process. Hot off the press, just a few hours ago, these were sort of finalised and well, look a bit better now. And cool, I'll wrap up in a minute. And we don't know necessarily how to read what is going on in these curves just yet. It looks like the decrease that is happening here is very similar to what we saw in our previous work in the developmental landscape, where there's some kind of layer norm collapse. But I think that if you were to perform the refined learning coefficient, like a learning coefficient estimation, you would start to get a much better picture of how this retreat from ridge is related to changes in internal structure as measured by the learning coefficient. So it turns out that all of the predictions we made were pretty much perfect. And yeah, I'll leave that up. These are the first steps towards understanding structural generalization, and I think these two toolkits